Hello, student. Welcome to this topic of physics experiment by simulation method. So now I am going to demonstrate another experiment, which is optics related experiment. So again, it is one more virtual lab. So we have to visit to the MHRD virtual lab URL or the website. So go to the Google and type MHRD virtual lab. So this URL is seen, and click on this virtual lab. So this website opens, which is maintained by Ministry of Higher Education, Government of Karnataka. As I told, so many experiments you can do or enjoy here by simulation method. So as usual, you go down, and here you'll see the broad areas of the virtual labs. And now the present experiment, what I'm going to explain here, falls in the group of physical sciences. So click on the physical science. So here on the left hand side here, you will see the list of experiments or the group of experiments which you can do. So again, I am interested in this laser optics. So I will click on this laser optics. So laser optics virtual lab is opens, and here are the many experiments listed which you can simulate and enjoy or check the concepts or results, whatever. So here, this experiment I am going to choose. This is numerical aperture of an optical fiber. So I'm going to demonstrate how the numerical aperture of an optical fiber can be determined by the simulation method. So when you click on that, the experiment on the numerical aperture of the optical fiber opens. So first, the theoretical part you will see, and this is done by the Amrita University. And here they have given one video also, you can go through it. So the theoretical part is given very nicely, and they explain what is the optical fiber. So this is an optical fiber. It is a transparent glass material which is used to transmit the light without the loss of energy. That is a very, very important point. So you can transmit the light through this optical fiber for a long distance without the attenuation. So attenuation is very, very less. So the light can propagate for a longer distance. So that is the specialty of these optical fibers. So the optical fibers are like this. And these optical fibers mainly works on the phenomena of a total internal reflection of light. That means when the light enters from one medium to another medium with certain angle of incidence, then at the point of incidence, the light reflects back to the same medium, and at the point of incidence, no loss of energy is observed. So the light comes back to the same medium after entering the second medium without losing the energy. So this phenomenon is called as the total internal reflection. So light propagates through this optical fiber based on the phenomena of a total internal reflection. So it is a tubular type of structure. It is a coaxial cable. Actually, the optical fiber is nothing but a coaxial cable. It is made like this. It consists of the two types of materials. You can see here inner one is there. This is called as the core or core material, and it will be having the refractive index N2. And this inner core is surrounded by another core that is called as the cladding. So these two materials, that means core and cladding, are made up of the same material. Only thing is that the difference between these two is that the refractive index is changing because of the density. The refractive index of the material changes as you come from radially outward from center of this cable. So the inner core circle is having one refractive index, whereas the cladding is having the another refractive index. Generally, the refractive index of core is greater than the refractive index of the cladding. So this is so because for the making of a total internal reflection, the light should travel from denser medium to the rarer medium. So that is the one of the condition for total internal reflection. So the refractive index of the core is made higher as that of the cladding. So here also you can see the cross-section view of this optical fiber. The center is the core and this is the cladding. And this is called as the refractive index profile. This is called as the refractive index profile of the optical fiber. You can see the refractive index is more at the core section, whereas it reduces at the cladding section. So this is called the step index mode of the optical fiber. So many things are explained. So you can see here. So light, you can see the two light rays entering the optical fiber. This is the optical fiber. This much is the core, and that is surrounding the cladding. And you can look at these two rays with the different angle of incidence. So this is this ray one. Ray 1 goes like this and gets reflected totally into the core again. Whereas you can see another ray 2, when it falls on the interface of core and cladding, it enters the cladding region. That means the second ray is not suffering the total internal reflection. So it is undergoing the refraction phenomena. So that should not happen because the light should come back to the core section. So that is why in this optical fibers, the angle of incidence is very, very important. So it should be below some critical angle, then only the ray will propagate through the optical fiber without losing the energy. So these are the some again theoretical parts of the optical fiber. They have derived that also very nicely. You can see here again core and cladding is there. So when this ray hits the cladding region, what happens? That is very, very important. Here the angle comes called as the critical angle. So here at the point of or at the interface of the core and cladding, when the light hits the surface, the angle of incidence should be more than the critical angle. So that then only it undergoes the total internal reflection. So that is also shown here. And here a cone is drawn. So all the light rays which are falling within this cone, they propagate through the optical fiber without losing the energy. You can see one ray is out of this cone. So when it hits the core and cladding interface, it do not undergoes the total internal reflection. So it is undergoing the refraction phenomena and hence entering the cladding region. So this should not happen. So that is why when the light is passed through the optical fiber, always a care is taken that the light always enter within this cone, and hence this cone is called as the acceptance cone. This is called as the acceptance cone. All the rays which are entering through this acceptance cones, they undergo the total internal reflection phenomena, and they propagate for a long distance. This is all the theoretical part of this optical fiber. And here is one thing we are defining called as the numerical aperture. So the numerical aperture is given by the square root of n1 square minus n2 square, where n1 and n2 are the refractive index of core and cladding respectively. So the physical significance of this is this numerical acceptance is that light entering in the cone of the semi-vertical angle IM only propagate through the fiber. The higher the value of IM or the numerical aperture, more is the light collected for the propagation of the light. Okay. So this numerical aperture means it is the certain value of the aperture when the light rays are entering through that aperture, they propagate for a longer time, or we can say that they are undergoing the total internal reflection phenomena. So that theoretical part is also given. So this is the theoretical part of this optical fibers, and you have studied, I think so. And second part, as usual, self-evaluation is there. And here will be some questions based on this optical fiber that you can check. You can check your knowledge here. And next part is the simulation part. So now we are entering to the simulation part. So when you click on the simulator button, this experiments open up. So once this is open, what we have to do, we have to click on this button to maximize the screen. So I click here, the screen gets maximized. Okay. And next, you remove this. Here they tell that to place the apparatus in correct order on the breadboard to start the experiment. Here breadboard is here. So the experiments are kept here in the rack. These are the experiments kept in the rack. You have to take one by one and keep on the this breadboard and do the experiment. So that is the meaning. So once you've gone through it, you remove it. And now I will start keeping the equipments one by one on the breadboard. Here is the one thing called as the emitter. Emitter means it is the source of laser which emits the laser light. So that you have to take it first, and it should be kept here. This is the first equipment you have to keep. Next comes the concentrator is there. Another equipment is there. Concentrator means it is having a concave lens. It concentrates the energy, light energy, so that it falls exactly on the optical fiber. So this is the second experiment, second equipment you have to keep. This is called as the second concentrator. Just you can click the mouse on there and drag it, keep it here. It comes in this way. So now I have kept the concentrator exactly before the laser source. And next detector is there. You can keep the detector. This is the detector is here, which detects the light. So the place of the detector is here. This is the place of the detector. And here fiber stand is there. That means to keep the fiber between the source and the detector, fiber stand is required. So you bring down this fiber stand and keep here. Okay. And next, current output meter is there. So here a sensitive diode is kept here. The detector is nothing but a photosensitive diode which detects the light, and accordingly the current is produced. That current is measured by this ammeter. So this is called as the current output device. You keep and you bring it and keep here. Okay. So all the things brought down except the fiber. Fiber is here, optical fiber is here. And this optical fiber kept at the end of all the equipments. That means after keeping all the equipments on the breadboard, you have to bring it down, this fiber, otherwise it will not come. Just I will tell you. So now I am bringing this optical fiber and I will keep the fiber into that position. So now the fiber is placed here. This is the source of light, and this is the concentrator. That means here the laser beam is made into a very fine beam. So that beam of light is falling on this optical fiber. This is the optical fiber. Now it is between this concentrator and this optical fiber stand. So here it is kept horizontally. So this light laser source which is emitted by this laser, this source, it passes through this concentrator, then falls on the optical fiber. So the light, the laser light passes through this optical fiber and it comes out, and here is the detector. That means here it falls on the a photodiode so that its intensity is measured. So this is the detector. So after emerging from this optical fiber, lastly it falls on the detector. Detector detects the intensity of light, and accordingly it produces a current that is shown in the ammeter. So now the experiment is ready to do. So you have to go to the right hand side of this experiment. Here start button is there. Click on the start button. So once you click on the start button, the experiment switch on. First you have to select this fiber. Different types of fibers are there. You select the fiber here. Just a minute. It's not working. Sometimes it happens like this. Now it is on. Okay. Once it is, this is off. This is off. Now you see no light is coming here. Now it is on. So you can see the light is falling on the detector, and now the current meter is showing 000 reading. And next click here to select the optical fiber. So first one you take the glass of fiber, and here you select the type of laser. So I will select the red laser. Next, coming to this point, here one thing is there, distance between the source and the detector. So distance between the source and detector is here. This is the source and this is the detector is there. So this distance we can vary. It is actually it is a distance between source and the optical fiber. It is here. It is this distance is there. No, you can vary it using this knob. This knob is that. So select this knob, and if you are moving this, you can vary the distance between the source and this optical fiber. So any one distance you can keep here, no problem. It works for all the distances. So just I'll keep some 2.5 mm like that. So now you can see that the distance between the source and the optical fiber is around 2.5 mm. This distance it is actually, and once this distance is fixed, you have to move the another distance. Another distance is that this is the this is the movement in x direction. Actually, he has given in written way, but this is the movement in I can say y direction. That means what is that? The source is moved slightly in y direction. You think that in x direction we are passing the light, laser source, and in y direction you are moving the source as a whole. So that is why two distances are there. One distance we are keeping fixed, means the distance between the source and the optical fiber is kept constant. But this distance you have to vary because the intensity of the laser falling on the detector varies if you are moving the source in y direction. So that is done here. So next you come to this part. Once you come to this part, you can note down here. And as you move, you can see here micrometer is given because you have to take the reading here. So here micrometer is given. So the least count of this micrometer is 0.01. And what happens, you see, here also arrow marks are given. So these are given to rotate the head of this screw gauge. Either you can use here or you can drag this circle to the right side to change the this distance x. Just I will show you. You can see here. You see, if I am moving this, you can look. You can look here. The reading is changing. It's changing. It changes. It changes like this. And also look at the ammeter. Now the current started to appear. The current readings are started to come. You can see. You see, in this way. So again it goes off, and you see as you move the distance slowly, current starts coming, or the intensity. What happens? Intensity goes on varying because the direction of the laser is slightly deviated because you are moving the laser source in y direction. So only when it is when the laser source is exactly at the middle of the optical fiber, quite naturally the intensity will be more. And when the source is moved little bit other side, intensity goes down. So that is the very simple concept. So you have to change this distance and note down this ammeter reading, current reading. So here you can see you can use this also like this. And you see when at the zero setting position, you can see here, actually it has to be here, but already it is showing a distance of 1 mm. So this you have to take as a zero distance because the reading starts from here. This is the least setting you can do here. So this is the zero setting of this micrometer. And now what you have to do, use this downward arrow mark and start moving the laser source, and you can move. Actually, as you move this one, you can see the current will not come immediately. You can see here I am moving. I using this knob, downward arrow mark. You can look at this ammeter. No currents are coming. Like this, current starts later. That's why current is zero up to certain readings. So you have to take here tactically. So what you have to do, you go on rotating the head scale of the micrometer by 20 divisions, then note down the ammeter reading. So that the number of readings will be less initially. So you can see here I will move the 20 mm. You see, now it is nearly 20 mm. I moved the 20 mm and current in the ammeter is 0. So again, I will go ahead. 20 plus 20 is 40. So now it is 40. Current is 0. So in this way, 20, you have to increase initially until the light comes. So another 20 like this. You go on rotating the micrometer by 20 divisions and note down the readings. And once the current, you can see now the current started to increase. Once the current started to increase, you should be slow. Otherwise, you will not get the maximum value, maxima. So that is why now you see the current started to increase from this point. So, once the current started to increase in the ammeter, what you have to do, you have to move the micrometer by 10 divisions. Before the appear of current, you will be moving the micrometer by 20 divisions. After the appearance of the current, you will move the micrometer by 10 divisions. So that is the very, very important point, so that the readings will be good. We can get a very good distribution curve. You can see here. And one more important point is that you can look at this meter. It is actually it is a nanometer. So many divisions it is giving. So and lastly, we have to express the current in microamperes. It is a nanometer. It is so many divisions it is giving. So once you got the readings, you have to convert them into microampere values. Adjust the readings to microampere values. Otherwise, you will find difficult in writing all these digits. That's a problem. So in this way, until the current increases and until it again decreases to 0, you have to move 10 divisions like this. You see now the current started to decrease. Continue until it goes to 0. In this way. So it's almost all gone to 0. So this is what you have to do in this experiment. So you have to note down the micrometer reading and this ammeter reading. So then you have to plot a graph of what is that? The distance traveled, x detected distance x versus the intensity. You have to plot a graph and you will find out the numerical aperture. So the experimental part is completed. Now I have taken a set of readings. I will show you. Now you can see by this simulator method, we have done this experiment. So the aim of the experiment is to determine the numerical aperture and the acceptance angle of the given optical fiber. And also we can determine the size of the laser spot here. So as I told, the least count of the screw gauge is 0.01 mm. And distance between the fiber and detector is 2.2 mm. Is there? That is fixed. And you can see here, we have taken the readings. Serial number, PSR means pitch scale reading, HSR means head scale reading, total reading of the micrometer. So initially you can see here we have moved a distance of 20, but once the current started, we have moved a distance of 10 divisions on the head scale. So in this way you will get the currents. These are the light intensity or the current reading that we have to express in microampere, and so these are the readings. These are the readings obtained. You can see as the current starts increasing from a particular value of X, it increases and reaches a maximum, then it decreases in this way. Then decreases. You can see again it decreases to least value. So this is what you have to note down the readings from that simulator experiment. And once you noted down the readings, you have to plot a graph. So this is the plot what I have done. So on the x-axis you plot the directed distance, that is d or x or d, so whatever it is, same thing it is on the x-axis. And on the y-axis you have to plot the current, which is in microamperes region. And you can see a very fine or nice distribution curve is obtained from the data obtained using this simulator experiment. And the current goes maximum here, then starts decreasing. And what we have to do here is that you have to determine the average value of the maxima, or sometimes it is also called as the IRMS value of the maxima. So maxima is here, it is around 30,000 microamperes. Maxima is here. To that maxima, you have to multiply 0.707. This 0.707 is nothing but the value of 1 by root 2. So I maximum by root 2 gives the IRMS value. So that is why this is multiplied. And once you multiply the I max with the 0.707, you will get some I value. So that you have to note down. In this case, it is here around 21,000 is there. So from that, you have to drop a line, horizontal line in this way. And this horizontal line cuts this distribution curve at these 2 points. From these 2 points, you have to draw the verticals to the x-axis. And these two are the verticals drawn to the x-axis. And you can see here, one line falls here, another line falls here. And the distance between these two x-intercepts gives the 2r. And this 2r is equal to 2r is related to the size of the spot. So the 2r is equal to some value, and r is equal to that value divided by 2 gives the spot of the laser here. So here one division is 0.2, it is 0.2, 0.2, 0.4 like that. So the value of 2r is, you see it is here, it is 0.2 and in a 0.3 and some little bit. So nearly 0.35 is the value of this 2r, which is noted down from this graph. Then you have to do the calculations. So from the graph, the value of 2r is 0.35 nanometer, as I told, that comes at the middle. Therefore, r is equal to 0.35 divided by 2 gives the 0.175 is the value of r. And from theory, the numerical aperture of the optical fiber is denoted as NA and is actually sin theta, which is given by r divided by square root of r square plus d square, where this r is the radius of that spot of the laser beam, and this d is the distance between the optical fiber and the source. distance between the detector and the source. So these values are put up here. The values of small r and capital D are put up here. The value of small r is this much is there. And the value of D, as noted down, is 2.2. 2.2 10 to the power minus 3. It is 2.2 mm, as I told earlier. That is also written here in the observation. So the distance between the fiber and detector is 2.2 mm. So that value we have to put here. So that is substituted. It is the value of R, and you simplify. This gives 0.0793. So which is nearly equal to 0.1. So you can Google out the numerical aperture for a single mode optical fiber, but you find that it is nearly 0.1. So here also we have got nearly 0.1, and hence the result is verified. It shows that the simulator works perfectly. Then using this, once you obtain the numerical aperture value, you can calculate the acceptance angle, which is given by theta is equal to sine inverse of numerical aperture, and this is equal to sine inverse of 0.1. So this comes out to be 5 degrees 7 minutes. So the acceptance angle is also obtained. So in this way, we did this experiment to determine the three things. We determined the numerical aperture of the optical fiber, which is found to be 0.1. And the acceptance angle of the fiber is also determined, which is found to be 5 degrees and 7 minutes. And the radius of the laser spot is also obtained, which is 0.175 mm. So these are the results obtained from this experiment. So in this way, you have to do this experiment. Okay, thanks.